which of the following organic compounds will give a mixture of 1-chloro and 2-chloro-butane on hydrochlorination? That means we have to find out the products here if you do the addition of HCl to these molecules. Okay, so if you have here, this is our alkene, and if we do the hydrohalogenation, means we are going to add here the hydrochloric acid, and we know that asymmetrical alkene, if you add a hydrochloric acid, then this addition will follow it's going to follow the Markovnikov's rule, right? So the double bonded carbon with more number of hydrogen atoms gets one more hydrogen atom. That means this particular carbon CH2 will be CH3 now, and the chlorine will go here. So the product in this case will be CH3, CH, CH3, CH, Cl, and this is the CH3. So this is 2-chloro 3-methyl, right? 2-chloro 3-methyl butane. So this is not a product. Okay, fine. So you can get the Markovnikov product and also the anti-Markovnikov product. So here in this case you won't get 1-chloro and the 2-chloro butanes, okay, because you get a 1-chloro 3-methyl butane and you will get 2-chloro 3-methyl butane here in this case, okay, because the other product will be the anti-Markovnikov product, that is the minor product here. Here in this case we have two double bonds here, right, at two positions. So here that means in this case you will get 3 HCl molecules. In this case there will be the addition of 3 HCl molecules. So here will be the addition of 2 HCl molecules. So this is not the case. This is not the case, right? So let's find out the products from here. If you add HCl now in this case, as per the Markovnikov rule, hydrogen will add to this particular carbon and the chlorine will go here. So that means you will get a 2-chlorobutane, okay? And when there is anti-Markovnikov addition, that's always there, but in the minor quantity, right? So that means the hydrogen will add over here and the chlorine will go to the terminal carbon. That means you will get a 1-chlorobutane. So if you add this molecule to this molecule, if you add HCl, you get two products. One will be the as per the Markovnikov product, the other one will be the anti-Markovnikov product, right? So one which is the Markovnikov product, that is the major product, and the other one is the minor product, correct? So that means in this case you will get the product will be CH2 Cl, CH2 CH2 and the CH3, and you also get another one CH2 CH3 CH Cl CH2 and the CH3. This is the Markovnikov product here, while as this one is the anti-Markovnikov product, right? And this is the major product here and this is the minor product here. So that means this is the option D, right? You get a 1-chloro and 2-chloro-butane. Here we got an alkene. You react with the NBS. NBS is basically N-bromosuccinamide, right? This is a brominating agent here. N-bromosuccinamide is a brominating agent, and it does the substitution at the allylic position to the double bond, right? So hydrogen atom from the allylic position will be replaced by the bromine from the NBS. NBS is N-bromosuccinamide, right? It's a brominating agent, provides bromine, and it is this bromine that will replace at allylic position. See, this is the double bond and this one is the allylic position, this is the allylic position, alright? So from the allylic position, this N-bromosuccinamide is going to replace the hydrogen atom by a bromine, alright? So this is a allylic position, this is another allylic position, so that means you can replace any one of the hydrogen atom from these two positions by the bromine and you get this product, alright? So that means the option A is there. Always it is at the allylic position, and the mechanism here is a free radical mechanism, right? From the NBS you get a bromine free radical, alright? You get a bromine free radical, and it is this bromine free radical that abstracts the hydrogen from the allylic position, alright? And if you get a hydrogen atom from the allylic position, now you have a double bond here, and so that means at this allylic position you will get a free radical. This is an intermediate that is formed when NBS, N-bromosuccinamide, it provides a bromine free radical that abstracts a hydrogen atom from the allylic position, and you get a free radical here. Now this free radical can undergo the resonance, right? This is under the resonance, okay? So you can have a resonance like this. One of the electron will be here. So you get another resonating structure. A double bond will be over here, and now you have a CH2 over here. And again it goes back and you get the first one back, right? So this is why the substitution only occurs at the allylic position, all right, the adjacent position to the double bond. It won't be from here because there the free radical is not stable. Here at the allylic position, the free radical is stabilized by the resonance. That's why the NBS provides, abstracts the hydrogen from the allylic position, right? And then the next step is, the Br free radical is going to attack at this allylic position, and you get this product here. Now, if you have a molecule like this, again the NBS is going to provide the Br free radical. Now it has two allylic positions, right? The two allylic positions are different. So you have a hydrogen here, and you have hydrogen over here and here. In this case, if this Br free radical abstracts a proton, a hydrogen atom, a hydrogen free radical from here, then you will get a tertiary free radical, right? So here at this position, you get a tertiary free radical. This is a tertiary hydrogen abstracting. So from this one, you get a stable free radical. The same Br free radical attacks here, and there you get a secondary free radical. Which is more stable? A tertiary one is more stable, right? That's why if you react this molecule here with NBS and bromosuccinamide, now the bromination will occur over this position, right? You get a CH3 here, and you get a bromine over here, right? So bromination is over here because the free radical, the intermediate form, it is more stable at the tertiary position. The tertiary hydrogen is basically, you can say, more reactive than the secondary hydrogen. This is the tertiary hydrogen, this is secondary hydrogen. Tertiary is more stable, right, than the secondary one. In this case, we have an alkene here, and you are adding the HBr. If we add the HBr, so what will be the product? It will be the Markovnikov product, right? So the product here is the Markovnikov product, and we know that as per a Markovnikov addition, hydrogen is added to the double bonded carbon with more number of hydrogen atoms. Alright, so the hydrogen will be here, and the bromine in this case will be over here. So that means the product will be like this, right? The product will be like this. The bromine will be in the middle here. Alright, so this is the A. And what will be the B? Here we are adding the HBr, but in presence of peroxide. When you are adding the HBr in presence of peroxide, obviously the product is anti-Markovnikov product, right? It's an anti-Markovnikov addition. Here it is the Markovnikov addition. That means in this case now, hydrogen will attack with the carbon having less number of hydrogen atoms, and the bromine is going to attack at the terminal one. So that means in this case, the product will be like this, right? It will be like this. Br is over here, so this is the B. Okay, so that means the option C here. A is this one and B is this. Now this is a multi-step reaction here. We have alkyl halide here. You react with the potassium hydroxide. See, we need to be a little bit very much careful in this reaction. When you react the alkyl halide with the potassium hydroxide in alcoholic medium, and the same reagent you react with the alkyl halide in the aqueous medium, there in the two mediums the products are totally different. In the alcoholic medium, what happens here, the hydrogen and the halogen is lost. Dehydrohalogenation occurs, so you get an alkene. If you react to the potassium hydroxide in alcoholic medium, alkyl halides undergo elimination reaction. Alright? Elimination reaction, because in alcoholic medium, hydroxide ion acts as a very strong base. So it is this hydroxide ion that takes the beta hydrogen atom, right? So this is alpha carbon and this is the beta carbon, right? It is the hydroxide ion basically that attacks the beta hydrogen atom, abstracts the hydrogen from the beta carbon, and what you get then? You get the water, and then the bromine is lost from the adjacent position, and you get in between a double bond. Alright, so that means if you react to the potassium hydroxide with the alkyl halides in alcoholic medium, potassium hydroxide in alcoholic medium, so elimination will occur, dehydrohalogenation will occur, right? So when hydrogen and halogen is lost from this position, hydrogen, and from this particular carbon, halogen is lost, so then there is a double bond in between. So what is the product? You get a product like this, CH3 CH double bond CH2. That means you got an alkene. So A, here is this alkene. Now when you react to the HBr again, the same reagent, same compound here, right? This A, you react with the HBr. Now what will happen? Addition reaction will occur. So Markovnikov's rule, right? So hydrogen will be here and the bromine will be over here. Alright, so then what you get? The B product will be CH3 CHBr here, and this is the CH3. So 2 bromopropane. And now again, if you react with the potassium hydroxide but in aqueous medium, now look at this one. Potassium hydroxide, as I said, in alcoholic medium is a strong base, while as potassium hydroxide in aqueous medium acts as a strong nucleophile. That means it will attack on this particular carbon and it will remove the bromine there from the alkyl halide. And then what you get? You get the CH3 CHBr CHOH here. The Br is replaced now and you get this one. Okay, so the product here, see here is, it is the propane 2-ol, right? It is the propane 2-ol. So the option A is here. Hope you got it. Thanks for watching the video. Bye for now.